We can now move to the next reproducibility paper, Fair Augmentation for Graph Collaborative Filtering, by Ludovico Boratto, Francesco Fabbri, Gianni Fenu, Mirko Marras, and Giacomo Medda. The presenter is Giacomo Medda.
Thank you very much. So the paper in question will regards indeed graph augmentation that aims to improve recommendation models, in particular graph neural networks, to generate fair recommendation towards consumer in particular. The idea started from the fact that most of the algorithms nowadays in the literature focus on approaches that work during the training, so they are in processing. But this quite typically work for specific models, while pre- and post-processing solutions have more benefits. This issue was considered in a recent paper that it was the objective of a reproducibility study, where they proposed a post-processing method to augment a graph and generate at the end a fair recommendation. Despite the remarkable performance that they showed and also the benefits of these approaches, there are still some issues, especially at the evaluation experimental setup and also in terms of formalization. Basically, the approach, we can say, takes the graphing input, generate the augmentation, and it should lead to fair recommendation during inference. So there's no retraining during this step. The main idea is to feed in input the graph into the graph neural network that is already trained, retrieve the recommendation, and then use a fairness-aware loss to understand how the augmentation should be improved. And this is all done according to the validation set during inference. So the augmentation goes like that, but you don't need to retrain the graph neural network. The issue that we found was first regarding the evaluation setup. Only 2 data sets, one quite small, lastFM1K, and only 3 models that right now are considered like baselines. And also the data set does not cover different diversity of domains and different things. Another important aspect of the reproduced work are this so-called graph sampling policies. Because of the augmentation needs to find edges around all the missing entries in the matrix, they try to propose some policies to sample the graph. So just take some user, just take some items, and let's see how it works. However, all of these policies are based on some empirical viewpoints. So they thought about important aspects in recommendation, and they try to see if the policies work. So they have not been formalized, and there's no a rigid description of them. And so, as a first, this aspect and other things that we will see, our contribution regard the formalization of these policies that we've seen, and also the formalization of the augmentation, I would say, algorithm. So how to see for each CNN and different architecture how the augmented graph impacts the utility and fairness. Then we extended the set of sampling policies, addressing some other aspect important, like the time dimension or graph common properties. We extended the experimental setup with a large number of models and also with different domains of data. And we also analyzed the overlap across sampling policies to ensure that each policies cover a different portion of the graph, and so we have different augmented results. So just to start, these are I would say, the formalization of the sampling policies they proposed. So these are just more easier to share with the community and understand what they do directly on the user and item set. It depends on some parameters. And the other, in the right side, you can see the formalization that we've done according to different architecture of graph neural networks. The first one about the common message passing neural networks, and the second regarding a particular model that uses singular value decomposition together with the graph neural networks. But there are not so many details here, and if you want to check out the paper, there are it goes more inside this aspect. The second contribution regard extending the sampling policies, because the time dimension is quite important in recommendation, especially if we consider the recency of the interaction, which are typically the ones that renovate the recommendation model. Second, the aspects, especially in entertainment scenario, where there are some the so-called timeless items, which are quite important because they are still like in the, I would say, important for the users and the consumer, and may impact the recommendation, the final recommendation. And at the end, also, we can see the page rank, which is a quite common and famous property that were not considered in the original study. We extended the experimental setup by first replacing Last.fm with a larger version with 1 million of interaction, and consider the location and fashion domain with Foursquare in Tokyo and New York, and Rent the Runaway about fashion domain. And we consider a quite large set of models that regard like subfamilies of graph neural networks. And you can see there are some models that are not augmentable. These models will be studied in a retraining phase, so they cannot be used with the method, but still are quite important for analysis. So the first results that we've seen, like, which is still a contribution because you regard the original sampling policies, is to guarantee that the sampling policies cover different graph portion. On the top row, you can see the user sampling policies, and we can see that according to the Jacquard similarity, there are at least 60% of users that are not, I would say, cross-found across sampling policies, even though a case is not really covered, the middle one, but it's just an exception. And the experiments regard 3 research questions. I will try to go a bit faster for the time. The first one regards the impact that the augmented graph has on utility and fairness. Given that we have 10 models, we destructed the table, which is quite big. And especially like that, the more important thing are the top values, the top column, the columns that regard the utility within the CG, and delta, which is a fairness level, we can say. This model does not perform really well because their architecture is quite, we say, sophisticated, more particular about graph transformer or singular value decomposition, and it did not work really well. But we still have 7 GNNs where the method that we reproduced worked really well. And especially, it's quite important, the last column, which is why we found the best GNN right now doing collaborative filtering. And the augmentation method was able to improve both the utility and also the fairness. All of this just during inference, without retraining. We also found an observation that on smaller data sets, the algorithm does not work really well, probably due to the fact that the validation and test set do not maintain the fairness distribution. We then consider how different policies affect the fairness level. So you can see directly on the top left of each square of each map the base value of fairness level. So if other values are lower than it means that it improved. The last two columns, Last.fm, Movlens 1M, worked better. So larger data sets are still affected better by the augmentation method. And also there is one policy that I would say improved better the performance. It was much more consistent. We also try to understand if the fair knowledge could be transferred. So just going a bit faster, we made some retraining with other models. First, the GNNs that were not augmentable, and so we trained with the augmented graph, and other models that are common in recommendation. But in general, briefly, we can say the method does not work. So if we retrain the models with the augmented graph, it does not get fairer, neither improve utility. So a conclusion, future works, we just want to share that we have a repository with better efficient GNN backbones that you can check at the end. I will share the source code. And there are still some future works regarding improving the experiments on transferability, improve the set of models, and also try to maybe find also explainability in this kind of systems. Thank you for your attention, and sorry for the time delay.
Okay, so unfortunately, we have run again out of the time, so we'll thank again Giacomo, and you can reach him offline for any questions. Thank you, Giacomo.